Yeah, hello, welcome also from my side. It's a big pleasure to be here. Yeah, I will bring maybe a bit more combinatorial flavor into this discrete optimization world. And I want to talk here about a kind of new research area which is called algorithms with predictions, learning augmented algorithm design. So I will talk not so much about achieving exact solutions, but more about approximations. And as a guiding example, I will mainly look at scheduling problems. So maybe a first check, who of you has ever worked with or thought about scheduling problems? Oh, okay, cool, quite a number. Okay, let me start. The way I like to motivate this area of algorithms with predictions, wonderful. The way I like to motivate this is by thinking about optimization in the real world, optimization under uncertainty. Now, in the real world, we cannot expect that we have precise input data always given. And there are many different ways of modeling this uncertainty in the input in traditional frameworks. And this is my personal view. I view this as there are three major frameworks. One we heard already about, robust optimization, so where we have given in some way described uncertainty sets, maybe scenarios, but other models would be, for example, online optimization or given online information, meaning that parts of the input data are just not given in the beginning, and then incrementally, while you're executing your algorithm, you receive more information. Or a completely other way of modeling uncertain input is to say, well, we might have given some stochastic information, some probability distribution, or parts of this. Okay, and the traditional frameworks would be then online optimization, robust optimization, stochastic optimization, with all kinds of flavors. All these models have in common that there is this uncertain information, but the type of information we receive is precise. Well, but now, if you think about all these data-driven applications, all the data we can access and we can process, and we have these big methods or very successful methods of machine learning, data science, statistics, we can get more information. Yeah, we can learn structure, we can learn inputs, we can learn all kinds of things. However, this does not come with a guarantee of the quality. Yeah, so right now, I mean, we cannot hope for getting the precise information, but all these frameworks that we usually use, online optimization and so on, they can handle only exact information, even if it's limited information, but whatever you get is precise. This would not be the case with machine learned predictions. So now we want to ask the question, can we somehow incorporate these imperfect predictions, for example, coming from machine learning, into algorithm design and still be able to prove rigorous, very strict performance guarantees? Yeah. Let me start with an example, and I hope here everybody will recognize a problem that we all know. Let's think about binary search. Okay. So in binary search, very simple. We are given, let's say, a sorted array of n elements, and we want to find the position at which a certain requested element sits. So this, let's say we request element 16, and I mean, if we look at this, we see this, but the question is, in a huge array, how do you find it? And I guess we all know binary search. So you look at your interval, you query the middle element, and you check, is the element we search for on the left side or the right side? So is it less or larger? And then we shrink the search space by seeing, well, my element is on the left side, so now my search space remains only here. And again, I ask the middle element, and again, the middle element, and so on, okay? So this way, by halving each step, my search space, in the worst case, it takes roughly log n many queries to find the element. And now imagine huge databases. So the searching, even logarithmic search time or queries, can be a lot. And the question is, well, don't we have sometimes an idea where roughly the element lies? Maybe we have a prediction that tells us, let's say the element sits in a certain position. Oops. Yeah, so this is now the situation I want to look at. And actually, I don't have only machine learning in mind. So I also have in mind, so if we search something, let's say we go to a library. It's a huge library. We search for a particular book. We have the letter or the name of the book. then we have roughly an idea of where our book could be, right? It's not that we really have to do binary search over the entire library. But let's say here for my big array there, I get a predicted position of this target element. What would be a natural way to use this prediction? Can you come up with an idea for an algorithm? What would you do if you have this information? Yes. So I predict a certain position and you would search before that position. First, I would go to this element and check whether this prediction is correct, right? Yes, that's what I would do first. So let's say I search for element 16 and I get predicted number, this position here. I check, it's wrong. Okay, so, but the first natural thing is to assume this prediction is correct and go for the lucky choice, right? Okay, so now we need to think about what do we do now? So we could say, well, from here now we do linear search. We just walk up towards our element. If my prediction is very good, meaning it's close to the actual position, then this is pretty good, right? So here in this case, how can we measure pretty good? We need some error measure. Yeah, so it's very natural just to take the distance between the predicted position and the true position. Let's say this is our error. If the error is small, then going to this element and then from here starting linear search is very good. But in the worst case, I go to the predicted position and have to walk all the way to the other end. So if the prediction is very bad, then this is a bad algorithm, right? It has search time n queries, roughly n queries, whereas a binary search could do in log n. But we can bring in this idea of binary search in the following way. We could say, okay, first we go to this element, and now we do kind of a reverse binary search to find, in this case, I see it's a lower limit for my search space, right? I could somehow in a doubling manner find a right end of the search space. And then it takes only logarithmic steps in this distance that I have to walk. Yeah, let's do this. So now this is very close now. So here I would now double my step size. I see 18 is already a right limit, upper limit, and then I go back and find it. Let me show an example what happens if I get a very bad prediction. So here, this is super far from my actual position, right? I do this doubling now. Now you see it better. I go 1 step, I go 2 steps, I go 4 steps, I go 8 steps. And now I see, oh, this one is less than what I'm looking for. I have limited my search interval. And now within this interval, I do my binary search. Again, logarithmic steps inside. Yeah, so this would mean now that if we wanted the guarantee, we could say, well, depending on how bad the prediction is, let's call this eta. Eta is my distance, is my error, how much off I am with my prediction. It takes me logarithmic many steps to find the other side of the search interval. And then in the search interval, which is roughly the error size, I do binary search. So again, logarithmic many steps to actually find the element. So I can say I have with predictions, I get a guarantee which is depending on the error of the input. And I need logarithmic many steps of this input, of this prediction, of this prediction quality. If my prediction is very small, if the error is very small, this is nearly optimal. In constant time, I find the right element. Yeah, if my prediction is bad, it's fine that my performance of my algorithm also is worse. What can I do, right? But ideally, this performance should not be much worse than if I would not have used the information, this prediction, logarithmic. And indeed, this can never be worse than logarithmic in n, the entire interval. Yeah. So this is the idea of the type of algorithm that we want. The algorithm should not use predictions. Let me write this here. I would like to design algorithms that have access to such predictions. They might be wrong, and the algorithm does not know this in advance. But I would like to design algorithms which now have an error-dependent guarantee, performance guarantee. And let me make this still a bit vague, but put down the kind of properties that I would like to have. Consistency. Consistency is what we call that an algorithm benefits really from a prediction if the prediction is correct. So if you look at my little picture here, so I will have here the prediction quality and here the worst case performance of an algorithm. Let's say this is the performance if an algorithm does not use predictions, okay? Then I want that if my prediction quality is very good, I expect that my algorithm is nearly optimal. It should perform much, much better than any algorithm that does not make use of predictions. Yeah, so here my guarantee is much better. It's fine if my algorithm performance gets worse, if the prediction quality gets worse. But at some point, there should be this robustness, this cutting point where we say, well, even if your prediction is arbitrarily bad, my algorithm still has a performance guarantee. And it should not be too much worse than if we would not have used any predictions. Okay? So this is the rough idea. It's a new line of research that I would say got reinitiated. I mean, flavors of this have been in algorithm design already before. But Likoris Wasowicki, they looked at online caching problems and came up with results there. And Kraska et al., they looked at databases and these kind of search problems. And this was only in 2018. And since then, it became a super vibrant research area. It's even difficult to keep track of what's going on there. If you're interested in this, there's a web page which keeps a repository of new papers that coming up. So together with my PhD student, we set this up, and now the community fills in their papers, and you can also organize and sort for certain buzzwords. So maybe that's a good starting point for finding literature. What I want to do today is I want to use as an example a very simple scheduling problem, or actually two scheduling problems, and then highlight a bit what kind of techniques can we use and what kind of guarantees can we get, okay? Min-sum scheduling is the following very basic scheduling problem. We are given a bunch of jobs, n jobs, and jobs are characterized by sizes. Yeah, I depict this by rectangles, and the length of the job reflects the size. And now let's say the task is to find a schedule on a single machine, meaning arranging jobs on a single machine, maybe preemptively, in such a way that the sum of completion times is minimized. Yeah, so schedule means at any point in time that can run only one single job. I can preempt jobs like here, this ping guy, he starts here, then we continue the job. And at some point when the total processing is done, then I have the completion time. And I minimize the average completion time, or let's say the sum of completion times. It's very well known that actually just sorting jobs in increasing order of sizes, that this is the optimal policy. Yeah, so intuitively, each job benefits from having only a small job in front of him. Yeah, so then by an interchange argument, you can show this. This works even slightly more general, even when the jobs have priorities. Let's say we have a weighted version where each job has its own individual weight. So high weight means, oh, this job is very important, you should put it early. Then there's, again, such a greedy or such a order of jobs, weight over processing time. So how much weight do you gain per processing unit? Ordering in decreasing order, this also gives the optimal policy. Okay, so it's an easy problem. And even if we have more complex machine settings, I don't want to go into detail here. I don't want to even define this. There are more complex, more interesting machine settings with multiple machines, heterogeneous machines. Even then, this problem is quite well understood. We cannot solve it in polynomial time anymore. It's NP hard, but there are good approximation factors. But in practice, I often do not know the processing time. Think of big data centers. They get these computation jobs and they don't know in advance how much time this will take, but they still have to allocate these jobs. How do you do this? So this is what we call non-clairvoyant scheduling. You're given this bunch of jobs, you don't know how long they are, how do you allocate them to your resources? We cannot hope to find an optimal solution. Yeah, I mean, processing times are unknown. What can I do? I know the optimal solution. So the optimal solution would be schedule in order of processing times if we stick to a single machine. Yeah. But not knowing the sizes, we don't know. So still we want to design algorithms and we want to assess somehow the performance of these algorithms. Here we use what we call competitive analysis. It's a worst case analysis. And essentially what we want to show is that our algorithm always finds a solution within a factor row from the optimum solution for any instance. What does it mean for us, for our minimization problem? Well, for our sum of completion time, I want that my algorithm for a certain instance, it has a sum of completion time, which is not more than row times the sum of completion times of the SPT order, of the shortest processing time order. And this should hold for any instance I, any of the infinitely many instances, okay? This is the type of bounds that we prove. So let me show you for this non-clairvoyant scheduling problem. It is well known that there is a nice fair allocation policy which is too competitive. Again, what does it mean? It obtains a sum of completion time, which is always not worse than 2 times the SPT sum of completion time, okay? And this fair allocation, this round robin looks like this. Let's say we fix some interval. And in this time interval, I want to share the capacity of the resource fairly among all jobs. That means each job receives the same amount of processing. Maybe some job completes in between, right? Because it's short. Let's say this guy completes. Then in the next interval, I drop this. I mean, this job is not there anymore. And then for the next interval, again, I'd say, let's share the capacity evenly among all the jobs. You see already that this discretization influences a lot how my jobs complete, right? So let's think of kind of this in a limit. So think about arbitrarily small, fine discretization. And in each of these infinitesimally small time slots, I share the processing evenly. I actually like to draw this in such a way that jobs run in parallel. They don't really run in parallel, right? But you can translate this into a very fine discretization, okay? So super highly preemptive, actually, you can debate whether this high preemption is what we want. But for this algorithm, we can show this factor of 2, this competitive ratio of 2. And let me show you how this works. I re-index jobs in such a way that the shortest job has the the index 1. No? And then increasing index means increasing processing time. Again, the algorithm does not know this. Yeah, it's only for the analysis. And now, well, which is the first job that completes? Well, it's the shortest job, right? They all get the same processing, so the shortest job completes first. Let's say it completes here. Its completion time is, it's its own size. But since it has had to share the resource capacity, it's stretched by a factor n, the number of jobs. Yeah, because it shared with n minus 1 other jobs. So I can write down the completion time like this. And the next job, well, the next job, let's say after this moment in time, in this interval, this is the second job that completes, its remaining processing volume, this is P2 minus P1, is shared with, well, in total, there are n minus 1 jobs left, so it has to share with these other n minus 2 jobs. And then you can write down the formulas, and let me not do this here. In the end, you can write this down nicely and even nicer, so this you can rewrite. What is written here? It says twice some weird summation. It says the first job, so the shortest one, counts n times, the second job n minus 1 time, the third job n minus 3 times, and so on, and the last job only once. This is exactly how you count the sum of completion time of the SPT order, the shortest processing time first order. Yeah, so this is exactly 2 times the sum of completion time of this optimum. Yeah, this is how we show these competitive ratios. Okay, so now I say, okay, this is the state of the art, and it's actually best possible for this simple non-clairvoyant scheduling problem. I say now, well, let's say there is given some prediction. I have machine learning tools that have seen many other previous instances, job scheduling instances, and they can predict to me the sizes. This is a very natural prediction. I wanted to show off a little bit and tell you that for more complicated problems, not really important, but I just want to tell for more complicated scheduling settings than the simple single machine, there are also such competitive ratios provable. Yeah, it's something nice. It's also some kind of fair share allocation. For very crazy machine models, you cannot do this greedily by hand. You have to solve some convex program. It's a bit more complicated. But anyway, let's say they're all nice, small constant competitive ratios. But if I go to, so maybe that's a nice link also to say, for me as a theoretician, I'm happy to prove here small, semi-small competitive ratios. If I go to a practitioner, someone who runs a huge data center, and I tell this person, well, you're off only by a factor 128 or a factor 5. I mean, this is not what they want to hear, right? This is infeasible. It's for a theoretician good to distinguish algorithms based on the worst case, but that's not what a practitioner wants to hear. And in fact, they have some more information. They have guesses on how long jobs are because they've seen similar jobs before. I will, from now on, I stick to PJ as denoting the actual processing time of a job. And YJ will be the predicted size of a job J. Yeah, so let's say I may overestimate the size, I may underestimate the size, I might predict the correct size, I don't care. Okay, so I will be given the set of jobs. I don't know the exact sizes, but I will see some prediction of sizes. And I want to make use of this. Again, talking about the error, so in order to express something quantitatively, the error for me is naturally the total sum of all these deviations, the under and overestimations. Yeah. What's a very natural algorithm? I mean, I'm blind. I see n jobs. They are indistinguishable for me, but I'm given the predictions. I should trust these predictions to some extent. Let's say I fully trust these predictions. That means it would be natural now to run the jobs in order of the predicted sizes, in increasing order of predicted sizes. If the predictions are correct, this is exactly the optimal order. Kumar, Purohit et al., they show that actually, even if the prediction is not correct, you can express the quality depending on the prediction quality. So they show that whatever is the sum of completion time of this shortest predicted job first rule, it is not worse than the optimum sum of completion times, plus some error-dependent term. So here, this is the L1 error of the prediction times n. So every job pays this error in the worst case. Okay. You can debate whether this feels good or not. Is it nice or not? For this algorithm, it's tight. And actually, again, if L1 is very small, so the prediction is close to correct, then this is just a small additive error term in the solution guarantee. If it's not correct, so if it's super wrong, if L1 error can be very, very huge, then this guarantee is meaningless, right? In fact, this algorithm can be arbitrarily bad. So using my notion of properties that I want, so here I would say it is consistent. Yeah, if the prediction is good, it performs very good, but it's not robust at all. So we need a trick to robustify such a algorithm. Okay, and for this, I want to show you what Kumar et al. Proposed first. They said, okay, suppose you have this algorithm which has a nice error-dependent guarantee, this follow the prediction algorithm, but it may fail. So you need to robustify it. You need to combine it with some other algorithm, which you know to be very good if you ignore predictions. This is my usual online non-clairvoyant algorithm, where I just showed you there are many results already known, small constants. And these two algorithms I want to combine. And I do this again in this time-sharing manner, in this round-robin flavor. I say so in a time interval, a certain fraction of the time interval, I run this good prediction-based algorithm. And in the remaining interval, to robustify, I run my online non-clairvoyant algorithm. And this, I have this parameter lambda. So someone has to decide how lambda is chosen, right? Which algorithm should dominate the other one. I will give you a guarantee that works for any lambda. And then we can give this to the algorithm user and say, well, depending on your trust in your predictions and depending on how risk averse you are, you choose the right lambda. Okay. And again, so I think about arbitrarily small time discretization, and I think of running both algorithms really in parallel, which is a bit cheating. Okay. Now, for the analysis, I don't want to write this down, but intuitively, it's, I think, easy to think about it like this. If I run my algorithm, the green algorithm, the prediction clairvoyant algorithm alone, so for 100% on the machine, then I have there is some guarantee, right? I assume that there is some error-dependent competitive ratio. Sum of completion time is at most rho times the optimum. If I now give the same algorithm, the same order of jobs, less processing capacity, it's like a stretch time. Yeah, so each completion time is multiplied by a factor 1 over 1 minus lambda. And similarly for this algorithm, whatever the guarantee is, each completion time is just multiplied by 1 over lambda. Time is stretched, it's delayed. And that's why one can prove immediately such a guarantee. So given an algorithm which has an error-dependent guarantee like this, and a robust algorithm which has this guarantee, then we combine both in our sharing algorithm and can state that the competitive ratio is the minimum of this quantity and this quantity. So the scaled competitive ratios that each individual algorithm had. Okay, this is a black box algorithm. It looks maybe scary, maybe not. I find it nice because it's really, I mean, you don't tailor it to one particular algorithm. You can plug in whatever you like. Let's plug in something for our single machine problem that I use here as a running example. Remember, for the single machine problem, we knew that if we have no predictions, then there's this two competitive round robin algorithm. And we saw on the previous slide that other people showed that the shortest predicted time first algorithm achieves a nice error-dependent guarantee. And if I plug them now together, I get this quantity, competitive ratio. And if you would like to see this maybe a bit more in the picture, I will choose my lambda. So for different choices of lambda, my curve looks different, right? If I believe that my prediction might be correct, no, then I would like to prefer this guarantee. That's a better guarantee. And I don't care so much if this beta is a bit worse. Then I would choose lambda small. If my prediction is correct, I'm close to optimal. I degrade in the performance. And then, so for this choice here, I would have a competitive ratio of 3 if the prediction is very bad. Okay, fine. If you don't like this worst case guarantee of 3, if you want this lower, then you choose a different lambda. Then you pay a little bit in the beginning. It's a bit worse, but still much better than the factor 2. And then you get a better robustness. Yeah, consistency and robustness here. Okay, this is the type of algorithm we would like to design. And one conceptually very easy technique, but even provable technique is to alternate between algorithms that benefit from predictions and another very robust algorithm. So one can think about whether this is a powerful framework and also applicable to other settings. And yes, it is. Yeah, so this is really in this learning augmented world. I mean, it's the easiest type of thing. If this works, then we're happy. For many problems, it doesn't work. But here in scheduling, in preemptive scheduling, we can apply this also to other problems. One should also look a bit more careful on the type of statement, the type of guarantee, this error dependency, n times the L1 error. And one can think about, is this actually nice? So even if my error is a bit bigger, every job pays for this. I don't like this error dependency with the n, the number of jobs in it. Yeah, that's not so nice. And if one thinks a bit more about this, somehow a linear error, no, this just a summation of these deviations and a quadratic cost function. So in a sense, quadratic, that we have the sum of completion time, where jobs contribute several times, may not be the right way to think about this. And there are alternative error measures. I will show one in a couple of minutes. And another thought is, do we really want to predict the entire instance? Isn't this a bit too much to ask? Or from another perspective, maybe less information is enough. We don't need all the individual job sizes. What is the crucial information? What is the, and this is problem specific, of course, what is the crucial information for a certain problem that we need and need to learn in order to profit really from this? So here's one idea. So in the scheduling world, I mentioned that the optimal order is this just order job by job sizes. And for other problems, this weighted order, weight over processing times. This is not only optimal on a single machine, even for more complex scheduling settings, and ignore my notation here. I just want to show for more complex scheduling settings, we may not get the optimal algorithm, but actually good approximations can be shown if an algorithm only knows the relative order of jobs according to some measure, but does not know the exact sizes. And this is something cool, and this is something we can exploit. So why don't we just predict an order of jobs? And of course, it must be trained a particular order. It cannot be an arbitrary order. So let's think for our single machine about this SPT order, the shortest processing time first order. Okay, so then if this is the correct sizes, then in other predictions, other error measures, they would have a big error for these predictions, this one and this one. But it could be that actually in terms of the relative order, according to the job sizes, the error is 0. Yeah, so that also means that whatever we count as error would be much smaller, much more concise. One can define, also don't read this, I just say it vaguely. One can define also based on a permutation, something, some new error measure. I mean, it's the L1 norm is somehow unclear. What does it mean for giving a permutation, right? You need to come up with something else. In a formula, we quantify what is the effect of a misprediction on an algorithm that makes use of this prediction. And this is what we quantify, okay? And then, yeah, this, so why is this a cool error, I think? Because it actually captures the structured real information that's important for the problem instead of some numerical values, which I don't even need really, okay? And then one can actually, again, go through our major framework and say, okay, first we need a prediction clairvoyant algorithm with some guarantee. And if you give me the correct WSPT order, it is the correct order. It's the optimal order. I use this as a prediction and I get a nice error dependent guarantee. And as a second ingredient for my sharing framework, this non-clairvoyant algorithm, I take black box from the literature, this round robin algorithm. Okay. And then one can combine using, again, this black box framework, we can combine these two quantities, this error dependency from here, and here this competitive ratio from here, and we scale it by the trust, this parameter lambda. Okay. In this idea, one can also apply to other machine models, which I now don't really want to show. Let's skip this here. Even on very complex, unrelated machines, it gets more complicated. It's not always so easy, but technically it's possible. Usually in my work, I look at these, I want to prove these performance bounds and then I'm happy. Usually I don't implement and try this out. But so here, when we did this, I was actually surprised how well, even on practical experiments, our bounds map to what we see in experiments. Okay, so let me not go into detail for all the curves, but I hope that you recognize here. So if I set my parameter in such a way that I trust a lot the prediction, then I get a very good performance guarantee, close to 1. 1 would be the optimal solution, right? And then if I have more noise in my prediction, yes, that degrades the performance guarantee. And yeah, I'm not sure if you trust me here that this actually now here is capped. There is a robustness, but maybe in the different curves you see this. If I only set my lambda to roughly 1/2, yeah, it's slightly worse if the prediction is correct. I don't find the optimal solution, but very close to optimum. And you see that then the robustness factor also is not so much worse than in the pure online world when I do not use predictions. Yeah, it's exactly what we would like to see as a guarantee. Consistency and robustness, and a nice error-dependent degradation of the performance. So in the last few minutes, let me show you a different example, online precedence constraints. So let's have in mind the same setting as before. We are given a bunch of jobs. We see that they have a weight, but we don't see much more about these jobs. Let's say they all have unit size for now. But there is some job volume that is revealed only when a job has finished. Yeah, so there might be other jobs that are revealed only once I have finished processing a job. So in the beginning, you don't see anything, all jobs look the same. So you start processing some jobs. Let's say the first 2 are these, and then there will be revealed, if they are finished, there's revealed some successor. This job again looks the same, right? It has weight 0, like all the other remaining jobs. So again, they're indistinguishable. You have to do something. You continue processing in some order. And there's one important job, this one. Since all of those look the same to you, you cannot distinguish. And in the worst case, you will do this pink job last. And only then is revealed that here's an important job. This guy has actually weight. So in the sum of weighted completion times, only this completion time will count. But this is a job that you finish last, which is super bad, because if you would have known in advance, so let me show you an optimum solution. If you would have known this in advance, you would do these 2 jobs first, pay only the weighted completion time of this guy, and then you're done. Yeah, so this gives a gap in the order of n. No online algorithm can handle such a situation and get a boundary or get a constant competitive ratio. But integrating learning, you can actually do this. And one idea is to predict the full instance. What if someone predicts to you the graph, the entire precedence relation setup? Then only in short, what you could do is, let's take this as input, trust it completely, and design your first algorithm. Remember, in this black box framework, we have 2 ingredients. The first is this error-dependent guarantee that you would wish from an algorithm that trusts the prediction. That's my first step. I could just follow the prediction, no matter what error measure you use. But then I need to robustify this, because this can be arbitrarily bad. And the second ingredient is, for getting robustness, I need some algorithm with some guarantee. So in this setting, in the online world, we cannot get any bound better than n, or better than graph dependent, maybe the width of a graph. So let me put here omega competitive, where omega is the width of the graph. Okay, it's essentially the n from the example before. And then this black box framework, this preferential time sharing, would directly give you this guarantee. Okay. And from here now, and this is something I will skip due to the time constraint, just to give you an outlook. So here one could actually now start thinking, do I want to predict the entire graph? It will not be correct anyways. But maybe even from the problem perspective, less information might be useful. What if I only predict maybe the weight hanging behind a certain node? No? The weight hanging behind this node and this node. This is complicated because you see the interaction, right? So the weight hanging behind the weight of successors of this guy intersects with the weight of successors of this guy. So it's not so clear how to decompose, but as an outlook, it is possible to decompose any DAG actually into out trees. And then one can get much more fine-grained and better guarantees and much less information that you have to predict. Yeah, so you will also only predict the weight of successors in a certain decomposition. But this only as an outlook. If you're interested, we can talk later offline about this. Let's skip this. Let me come to an end. So what I wanted to highlight here is this new line of research on called algorithms with predictions, algorithms that integrate these imperfect predictions into algorithm design where we aim for hard worst case guarantees. Yeah, and I've defined to you this consistency or robustness setup. I showed you a powerful time-sharing framework. We discussed a little bit that one should think twice about what's the right prediction model, and you should also think about what is actually learnable. You should think about what's the right error measure that makes sense for the problem. And as an outlook, this was only a very simple technique, this sharing, flipping forth and back, switching between algorithms. There are many more and other techniques, and I would be happy to talk more about this, but not here and now. And this idea I showed you only in the context of online optimization, but of course, you could improve any kind of performance measure. Think about running times of algorithms offline, or think about improving the update time for dynamic algorithms, improving the price of energy in mechanism design, or pick whatever you like. In robust optimization, improve the guarantees you get there. So it's a big world, it's open, it's quite new, and there are many, many things still to do. And here I want to close my lecture and thank you for your attention.